Okay, thank you. So it's wonderful to be back here again. I see it's developed a lot. Okay, I'm going to give you, I've got too much material in this talk and it's partly actually in flux. So I'll see what I can cover, but I want to basically emphasize two things: a reinterpretation of flux attachment as orbital attachment, with the recognition that what is flowing in quantum Hall effects, both in Landau levels and in Chern bands, are local orbitals. And for Chern bands, the new feature which is recognized, Chern bands, of course, don't have 1A orbitals, as you know, but they do have local orbitals which can move, while 1A orbitals are glued down to the lattice. And so this is going to be and in fact, the Středa relation shows you, when you think about it clearly, shows you the mobility of the local orbital basis and how the density can change. And the other thing I want to talk about is these local orbitals, or the structures that flow. The local orbitals plus the charges they carry are not point charges. They are quadrupolar. They have a quadrupolar charge distribution, and I'll tell you what that is. Okay, thank you. Okay, so this part of this, you don't need to, this is of course going to be a theorist talk, so I'm not going to talk about real systems, which look more like this. The theorist toy model system is a nice, clean, incompressible bulk quantum Hall fluid with some nice edge states. In the real system, charge neutrality forces the edges to kind of percolate through the system, and something looks like this, but the theorists like a toy model like that one. Okay, so yeah, basically the second point is that the recent discovery of flat band fractional Hall effect in Landau Bloch systems without a magnetic field, fractional Chern insulators, really provides the opportunity to go back and re-examine our ideas about the fractional Hall effect, integer Hall effect too, and throw out details which are specific to Landau levels but not present in the other system as not being fundamental to the phenomena. And that is a new opportunity. And okay. And another thing is that no one has really addressed the energetics of quantum Hall systems. Laughlin provided a model wave function, and as far as I can see, the main reaction to that has been, it's a clever wave function, it works. But why it works, nothing beyond it's a clever wave function that keeps the particles apart. It's not really a scientific statement, it's just a rationalization. So the energetics rather than the topology is a kind of part of the quantum Hall that's not been really properly addressed. Okay, and the other thing is, Laughlin actually told us the quantum Hall effect was an incompressible quantum fluid. But the notion that it's a fluid has not really been properly addressed either. And an interesting but long delayed thing about the fluid mechanics of the quantum Hall came when the Hall viscosity was introduced in a very kind of formal way back in the 90s. But the term viscosity ought to tell us, wait a minute, that's a fluid property, and indeed a crucial part of the fluid dynamics of the quantum Hall can be addressed. Okay, so I'm going to make a point about using indices in their proper places. Let's not go through that, but basically upper indices will be, so I'm not going to use the metric of space, which is only a property of the Cartesian coordinate system as far as condensed matter is concerned. I'm going to put the indices in the right places without moving them around, and that will help to help things. So let's just move on from that. Okay. The other thing, the quadrupole. Most people don't really know what a quadrupole is. They learned it in electromagnetic classes, and they were interested in the 1 over r to the 4th field of two dipoles put back to back. But the quadrupole is more than that. The quadrupole is the second moment of the electron distribution. It's not a traceless tensor. The quadrupole definition I'm going to use is this one here. There are actually 4 definitions in the literature, depending on whether it's so-called primitive or whether it's primitive or so-called traceless, and whether you put a factor of a half to. The important piece of importance of the quadrupole will not be in the electric field it produces at large distances. It'll be in how it couples to the local electric field. A monopole couples to the local electric potential, a dipole couples to the local electric field, a quadrupole couples to the local symmetric gradient of the electric field. Okay. And so why this is why people the so-called traceless quadrupole is really just a part of the quadrupole which is not congruent with the dielectric tensor, because any part of the quadrupole that matches a dielectric tensor or the permittivity tensor doesn't produce a long-range field. Okay, so if you're interested in a long-range field, you can throw that part away. If you're interested in energetics, you cannot. Okay, so let's just go through that. So let's look at the quantum Hall effect again. Condensed matter has 3 subsystems: lattice, something to do with the Fermi surface, the electronic part, and the electromagnetic part. In incompressible electron systems, the electronic system is gapped. So the only low energy degrees of freedom are the lattice or electromagnetism. Lattice phonons and photons or polaritons. So usually if the electron system is incompressible or gapped, it means it's a band insulator. The electrons are owned by the lattice, in which case they have no low energy independent degrees of freedom, and their density is fixed by the local density is fixed by the local Bragg vector fields, because in an insulator, the volume of the density of the electrons is proportional to the volume of the Brillouin zone. So what happens in the quantum Hall effect is some of the electrons are stolen away from the lattice by the electromagnetic field. Okay, so in quantum Hall, electrons on a lattice plane, the electrons still remain localized and bound to lattice planes, a single lattice plane, but they can move when Landau quantization occurs, which is captured by the electromagnetic field. The electrons can move in the whole plane, the plane in a particular lattice plane. And and so they will flow with, essentially the leading order in their flow velocity is just the drift velocity, and that's completely dictated by the electromagnetic field. So it's not a fluid with an autonomous flow velocity. It's a fluid with a flow velocity that's dictated to it by the direction, the system of which is directing it, the electromagnetic degrees of freedom. Okay, and the mechanism for capture is Landau quantization. And Landau quantization has the effect of removing umklapp processes. If the electrons are Landau quantized, they're in energy levels which correspond to closed orbits in K-space. And so since they go around in an orbit around a fixed point, the momentum doesn't change, and umklapp process is suppressed. So they lose connection to the lattice, at least the lattice plane in which they're free to move. And crystal momentum can be retreated as true momentum, and we can work in a continuum model which doesn't see the underlying lattice anymore. Okay, so we have quantum Hall effect. So quantum Hall effect, of course, was a huge discovery. I'll talk about it a little bit later. It took us some time to understand that it was topological. And this is the standard picture for the quantum Hall effect. The simple kind of thing that you have electrons going around in fixed Landau orbits of a fixed radius because of the quantization in the bulk. But if the Landau orbit radius gets close, if you're closer to the edge of the system than the Landau orbit radius, you collide, and then there's these one-way edge modes. And the one-way edge modes are the key feature of the topology of the quantum Hall effect. We should have recognized it right away. Initially, people spent a lot of time proving quantum Hall effect would come from disorder, pinning things. But really, you don't need any disorder for the quantum Hall effect. You just need a container with edge states. Certainly, if the states don't percolate through the bulk, the plateaus will be narrower than they would be in the real case, where the edges are a larger proportion of the system. But of course, just pinning the Landau level, pinning the Fermi energy at the somewhere in the edge states is what gives you a range of magnetic fields in which you can see the quantum Hall effect. This picture is actually a very interesting picture. First of all, the key feature it shows is that, of course, as the edge states go around, they have a periodic boundary condition that's modified by the flux through the bulk, which has the effect of pumping electron orbitals into and out of the system through the edge. This will be the Středa anomaly. And the key thing this shows is that the orbitals in Landau levels are mobile. Of course, they're not pinned to anything. So the orbital density goes up and down with the magnetic flux through the bulk. And the charge density is just slave to the orbital density, because as the orbitals in an integer effect flow through the chemical potential, they pick up a charge. But the key thing this is showing is that orbital flow occurs. And the fractional the Chern insulators also have the same feature, which immediately shows that orbitals flow in Chern bands too, which is why they're fundamentally completely different from trivial block bands with Wenny orbitals. Okay, so let's see, this is what I just said. So in the Landau levels, the local orbitals that the electron occupy can be characterized as the guiding center. So the guiding center is really the anchor on which the local orbitals sit in the Landau level. And the electrons are bound to the guiding centers because they go around the guiding center in Landau orbits. And it's the guiding centers that flow in response to the electric field. The guiding center flows at right angles to the electric field, and it carries with it the charge. Okay, so quickly, let me just go over the decomposition of the spatial coordinate in our Landau levels. So in Landau levels, we can decompose the coordinate of the electron into the guiding center plus the Landau orbital radius. So basically, we can define the guiding center by subtracting the Landau orbit radius vector is just given in terms of the dynamical momentum, and we can subtract it from the electron coordinate to define the guiding center. And actually, to define this more cleanly, we impose the condition that in each Landau level, the mean expectation value of the Landau orbit radius vector is 0, which fixes the center of the orbit to be that. That may be trivially obvious for if you've got some inversion symmetry, but in general, Landau levels could be centered at arbitrary points in K-space, and it's an important point. So there's an ambiguity in you have to define exactly how we partition the electron coordinate into the guiding center and the Landau radius. And the key thing is that while the electron coordinates commute with each other, the Landau radius vectors and the guiding centers have equal and opposite commutators, and they commute with each other. And once you quantize the Landau levels, only the non-commuting guiding centers remain as dynamical variables. So within the Landau level, fixing the Landau level state, we can define a basis of the positions of the guiding centers using a quadratic form. So usually this would be just r squared, but it's important to notice there's an arbitrary quadratic form defined by a Euclidean metric with determinant 1. So I take a quadratic form and I center this at an arbitrary point. So I've got a basis of states of the Landau level, which you can go up and down with harmonic oscillator type raising and lowering operators. And the Loftlin state can be actually defined. The Loftlin state, we can focus on its structure within the Landau level itself, so just as a function of the guiding centers. And the Loftlin state actually contains within itself a hidden parameter. It depends on the metric that was used to define these operators. Usually you'll see these operators as just Z or Z, since I've been Americanized, Zi minus Zj to a power Q. But Z is really a dagger, the raising operator, which pushes you outwards from the center of this basis, onion ring style basis. So the Loftlin state actually contains within itself a hidden geometric parameter. Now, if Q is equal to 1, it's a filled Landau level. The filled Landau level is a unique state. It doesn't matter what basis I represent it in. So the filled Landau level doesn't depend on this metric choice, except if I keep the number of particles finite, when it will define the shape of a droplet or filled Landau level. But it's fundamental to the fractional cases because it will define the shape of the correlation hole surrounding each electron. So in a filled Landau level, the charge carriers are empty orbitals which flow in response to an electric field. Again, this is the guiding center flowing without an electron attached to it. And so this is one of the basic points will be the empty orbitals are a new degree, a mobile degree of freedom in the Hall effect, fractional and integer. And the most remarkable property of the Hall effect is the Středa anomaly, which I call the Středa anomaly, which is the Středa relation, but that tells you that is not so much the relation between electric field and electric current, which is quantized. It's the relation between electric charge density and magnetic flux density, which is quantized. This is the Středa relation. The Středa relation tells me now I'm going to prefer to use the Faraday tensor rather than the vector B field, which is a pseudo vector, because the B field depends on choices of right-handed or left-handed, an arbitrary choice of plus or minus of orientation. And in two-dimensional systems, that's led to a lot of confusion. Is the field up or down or whatever? So we'll work in terms of the Faraday tensor, which is the fundamental representation of the magnetic flux. This tells you that which is antisymmetric, of course. It's just the d by dx of ay minus d by dy of ax. So if I take the derivative of the charge density with respect to the Faraday tensor, that's purely the antisymmetric part of the Hall conductance. This is purely topological and non-dissipative. In fact, if I take the Středa relation, take a time derivative of the Středa relation, and then do a spatial integration, I pick up an integration constant, which is the symmetric part of the conductivity. So the conductivity has the topological and non-dissipative part, but it also has an ohmic dissipative part. This relation has no dissipative content to it at all, and it's fundamentally topological. Okay, what about fluid dynamics? This is actually kind of interesting because it hasn't been exploited in the past. So unlike the fictional incompressible Euler fluid, which is a model of an incompressible fluid that it's got an infinite sound velocity, so it violates relativity, it violates causality. It basically has pressure equilibrates instantaneously in the Euler fluid, which is kind of like Newtonian gravity. If some heavy object suddenly gave an impulse to the sun and it was gone, we know it immediately in Newtonian gravity. It takes 8 minutes for us to know about this devastating problem in Einstein gravity. So Euler fluid has an infinite sound wave, and it supports pressure. It's got its own autonomous fluid velocity, which, when you solve the equations, has finite time in singularities, all kinds of stuff. But the quantum Hall case is a true quantum incompressible fluid with none of this causality violating stuff, because it does not support sound waves. It's got a quantum gap in the bulk. This means actually the fluid does not support hydrostatic pressure. It does not transmit any force through its bulk, and the only way forces are transmitted if you push it around the edge. So I can make a maximum density droplet of a quantum Hall liquid by taking this basis I described earlier, this concentric circles or ellipses, and fill them up to some particular radius. So I've got a nice little droplet of quantum Hall fluid. I can put it on the plane with no external potential, just a flat plane. It will just sit there. It won't expand. That's telling you there's no pressure inside the thing that would cause it to expand. Okay. Kind of like an ideal Bose condensate has no pressure, but that one's fundamentally completely compressible. This is an incompressible fluid that doesn't expand. So if there's no pressure, what happens if the confining potential tries to compress the fluid? And actually, I only realized this, I've been teaching engineering students on Physics 104, which is the basic introductory physics, and we're doing all the electromagnetism. And in fact, this picture, I haven't seen the following thing. You see the traditional skipping orbit picture. Of course, you know that every time the orbit hits the container wall, it's giving it an impulse. So this edge current is actually pushing outwards on the wall. And what is it? It's actually the Lorentz force on the edge current. As there's an edge current going that way, there's a Lorentz force pushing outwards. And indeed, that's the way the system responds to external pressure. If I put it in a container, I've got some potential wall on the outside, I'm pushing it inwards. What happens when I squeeze it? There's no pressure to go up, so it's not behaving like a standard fluid. I squeeze on it, the pressure goes up until the pressure inside balances the external force pushing on the walls. Here I try to squeeze it. As I squeeze it more, I drive a larger and larger edge current until the Lorentz force outwards on the edge current in the magnetic field pushes back on me to balance the compression. So just the standard BIL force that you teach in elementary electromagnetism is actually the fundamental mechanism the quantum Hall system has for against compression. And a more careful analysis of this shows there's actually two distinct responses to squeezing by the external confining potential. The first one, the obvious one, is the electric field itself, which just causes a flow. But the underlying thing in the Landau level, the electron going around the guiding center has no dipole moment relative to the guiding center. It doesn't carry any polarization. And in fact, the fundamental gap in quantum Hall systems in their bulk is a gap against anything that carries electric polarization. Okay, they have a unique state, which is and then there's a gap for anything for electric polarization. So the electric field effect is a second order response. And it's actually an Landau level mixing response, it calls. So the electric field just pushes the center of the orbit downstream from the guiding center, giving a dipole moment, electric dipole or polarization to the Landau orbit. But it's a second order effect in the electric field. Turns out the response, but on the other hand, the response to the second derivative of potential or the gradient of the electric field is a first order perturbation response because the undeformed Landau orbit has a primitive electric quadrupole, the second moment of its charge distribution. There's no first moment of the charge distribution in the uniform state, but there's a second moment, and that's a fundamental part of the quantum. Turns out to be a completely central and fundamental part of the fluid mechanics of quantum Hall systems. So there's a first order response to the gradient of the electric field, which will turn out to be the Hall viscosity response. There's also a second order response to the gradient of the electric field. It actually causes the shape of the orbit to get deformed and get compressed along the direction of flow. This one just displaces the orbit without changing its shape. This one, the second order response here, changes the shape of the orbit around the edge. So, okay. So let's see. So anyway, quite a lot of interesting features arise from that. So we can actually, what we actually need to do is let's see if another slide has anything in it. I probably didn't put it in there. Okay, let's go back again. So the key thing is actually to find the energy of the Landau level as a function of the external potential, because what is driving the flow of the Landau levels is the gradient of the Landau level energy as a function of position. When I put on the external potential, the first effect is just to raise the Landau level. So the first effect is to shift it just by the external potential. But the second order effect, I actually have to. This is what I'm doing. I'm taking an external potential as a function of r, which is a function of the kinetic energy is a function of the Landau orbit radius vector alone. The external potential is a sum of r, which is the sum of the guiding center and the Landau orbit radius vector. And actually, what I actually want to find is the formula for the Landau level energy of Landau level n as a function of the guiding center. Okay, and you just do that by straightforward perturbation theory here. We see that this is the rising of the Landau level by the external potential. This is the coupling to the electric field. This is a electric dipole, and this one will be the electric quadrupole, coupling to the gradient of the field. And interestingly, the second order response to the electric field could be, of course, is a quadratic response to the electric field, which is of this form here, chi e squared. But I could do a kind of Legendre transformation and write it as E dot P plus a half times the E squared. But if I rewrite E as B over V, write the velocity flow to lowest order as E over B, you can see that this extra term here is essentially a Galilean-like kinetic energy. If these are P squared over 2m Landau levels, it's indeed the mass term entering here is exactly the Galilean mass, but in principle, depending on the dispersion relation, each Landau level has its own Galilean mass, okay? So a long-standing problem of this was, so this is showing how actually Landau level mixing, which this effect is actually should actually be incorporated in a much more profound way into the theory of the Hall effect. And the issue about what the Galilean mass and stuff like that of Landau orbits is partly solved by that. Okay, so let's skip that. The other response is the Hall viscosity response. So I'll give you here a recent formula for the Hall viscosity. So the Hall viscosity was introduced by Avron and Seiler and Zogarov around mid-1990s. And it was a rather obscure thing at the time, because it was actually, unfortunately, phrased in a very obscure way. But it's a fundamentally, the first part of their calculation is a beautiful calculation. It's much more beautiful than the way they present it. I won't go into that, but basically, one can now rationalize this thing and remove certain, they specialize too early to Newtonian particles, and we want to avoid using the Newtonian masses and stuff like that. The general formula for the Hall viscosity is just, it's odd, it's antisymmetric under interchange of the first two indices. I guess, let me just say this, the relation between stress and viscosity is given here. As I said, I'm insisting on putting indices in the right place, so the stress tends to have one upper index and one lower index. With due apologies to Mr. Cauchy or Monsieur Cauchy, we're not imposing continuous rotational symmetry of Newtonian mechanics on this system, and so the nice tricks involving the metric and lowering them, which make it symmetric, are kind of not valid as a general principle. Okay, they're valid if you have rotational symmetry, but we're assuming that the background of this thing is a lattice somewhere or other, and we don't. In condensed matter, there's no such thing as continuous rotational symmetry. Okay, so So the stress tensor looks like that. The stress tensor is traceless because that's telling you the pressure is, there's no pressure in quantum Hall fluids. And it's also, because it's gapped and dispersionless, gapped and dissipation free in the zero temperature limit, eta becomes antisymmetric in that limit. The simple formula actually is a combination of the magnetic flux, which is odd under time reversal, because this is so-called odd viscosity, and the density of electric quadrupoles, the quadrupole density, which has dimension of electric charge in 2 dimensions. And this is a very intuitive formula when you think about it, because the quadrupole is what couples to the gradient of the electric field. The viscosity is what couples to the gradient of the flow velocity. To leading order, the flow velocity is the electric field divided by the flux density, and therefore the gradient of the flow velocity is the gradient of the electric field. Okay. So this is this is a very revelatory formula. It was for me, and this actually shows up immediately the importance of the quadrupole density as a fundamental aspect of all quantum Hall systems. Okay, a fluid with a quadrupole density is quite interesting. If you have a polarization density in the bulk and it terminates, you're going to get a charge density on the edge. If you have a quadrupole density in the bulk and it terminates, you get a polarization density on the edge. So that there's actually a nice bulk boundary relationship between dipole moment on the edge and the quadrupole in the bulk. Unfortunately, that's ruined by the other effect I said. The Landau level mixing effect also produces dipoles on the edge. So if you allow Landau level mixing, you've lost the bulk boundary correspondence. But if you project completely into a Landau level, you will find there's a bulk boundary correspondence between the quadrupole density and the surface dipole charge density, edge density. Okay, so here you see the surface dipole in the inter-Hall effect is just coming from the shape of the Landau orbits, which is what gives you the quadrupole density, because the guiding centers may terminate directly at the edge, but there's each guiding center has a Landau orbit around it. In the fractional Hall effect, the guiding centers themselves have a quadrupole effect, and you see that there's excavation of density inwards at the, for example, at the edge of the Lofton state. So we see actually they have opposite sign quadrupoles, because they have opposite sign edge densities, the Lofton, the guiding centers, and the things. Okay. So new ideas are going to be that the formation of the quadrupole, I believe, is the key to understanding the energetics of the fractional Hall effect. Let's see, there was another picture here somewhere. Okay, let's go back again. So anyway, so I'm going to say that the quadrupole is fundamental, and in the fractional Hall effect, there's an emergent quadrupole formed by orbital attachment. And in fact, that quadrupole has a Goldstone mode. That orbital attachment has a Goldstone mode going with it. It's a gapped Goldstone mode because there's actually no broken symmetry. Goldstone modes don't need to have broken symmetry. Goldstone modes occur when a new dynamical degree of freedom emerges. If I have a ferromagnet and I cool below the Curie temperature, I start to have magnons or spin waves, right? And if it's an isotropic ferromagnet, those spin waves are gapless. If it's a ferromagnet, they have a quadratic dispersion, go to zero quadratically. If I now put on a small Zeeman term to my ferromagnet, that doesn't destroy the order parameter. That causes it to preferentially line up along the Zeeman field direction. And now it's gapped because the order parameter wants to stay close to the Zeeman field. But it's a degree of freedom that didn't exist above the Curie temperature. It's a new degree of freedom. So it's a mistake to think that Goldstone mode has to be gapless. It's only gapped. It's still there, but slightly gapped if you break the symmetry of the system. Okay, and this same thing happens here. The polarization is okay. So it'll turn out that the Gervin-McDonald-Platzman mode at long wavelength is the Goldstone mode of flux attachment, of orbital attachment. Okay. So the foundation of our, okay, what does that mean? Okay, good. So the foundation of our understanding is the Laughlin wave function, and this was usually interpreted as flux attachment, but I'm reinterpreting it as orbital attachment. Okay, so there's the cartoon for flux attachment. When you think about it, it's a kind of crazy picture because the flux isn't bent in any way, right? So people say, well, it's really vortices or fluxoids or vortices attached, but we're going to actually look at this again. So churn bands, there's no flux involved. People say, oh, there's some effective flux. No, there's no flux involved. So the flux attachment is an absolutely lousy idea to apply it to fractional churn insulators with no magnetic field. But in the Landau level, there's one orbital for each quantum of flux. So actually, you get a very simple transition from the notion of flux attachment to orbital attachment. So let's pass this. Let's go back to this stuff. They're just telling you why we should do this. So again, I emphasize this kind of onion, this basis within a Landau level, this onion ring type basis, where it's really not circular, but necessarily circular, but elliptical orbits parameterized by a quadratic form centered on some arbitrary point. And there's one flux quantum passes between each of these rings I put here, right? So this onion ring basis is crucial for understanding the Laughlin state. The Laughlin state has the feature that it's got a metric, so I have to use the onion ring basis appropriate to the actual metric, which is a parameter of the Laughlin state. In that basis, if the central orbital is occupied, the next two orbitals are empty. And each of these orbitals is actually, in this chiral onion ring basis, is an edge state of the region it encircles. Okay, and that will be true. There's an analogous onion ring basis in churn insulators, but not in topologically trivial Bloch bands. Okay, so what you see here is that you can basically say, rather than saying this has a vortex attached to the electron, I'm going to say this electron is occupying 3 orbitals or attached to 3 orbitals. So that's a much simpler way, and that's a language which translates immediately to the fractional churn insulators. So we can say, you can either say this electron is occupying 3 orbitals, because in the Laughlin state, if the central one is occupied, there is 0% chance of any of the other electrons being found in that set. Or I'm going to use a language, I'm going to say that 3 orbitals are attached to each electron. Okay. So this is the language change I'm proposing. So let's look at this a little bit more. So a key thing is that the orbitals can be moved, right? So in fact, the Chern-Simons gauge field picture is actually, it's not describing electrons, it's actually not describing composite particles, it's actually describing orbitals. The Chern-Simons gauge field is actually a 2+1 dimensional gauge field. And the orbitals are the electrons are free to move in 3 dimensions. They don't have to spend their time on this lattice plane. They can hop away, and they couple to a 3+1 dimensional gauge field, the electromagnetic field. The orbitals are completely 2-dimensional. They can't live, the orbitals only live in this lattice plane. The orbital itself can't jump, right? The orbital is only there, this empty orbital is only there because most of the other orbitals in that lattice plane are filled. So the orbital is a 2+1 dimensional object. It couples to a 2. As it moves, it picks up a Berry phase, because if I think of a filled Landau level first, the filled Landau level is a Slater determinant of all the other occupied orbitals. I can choose any basis for that Slater determinant, except none of the orbitals in that Slater determinant, they don't have to be orthogonal to each other, but none of them can, but they all have to be orthogonal to the empty orbital, otherwise it wouldn't be empty. So moving the empty orbital around is a huge shakeup of the Slater determinant, and of course it produces a Berry phase. And this is what Arovas, Wilczek, and Schrieffer did. It shows that the Berry phase can maintain it. You take the path of the orbital, you count how many electrons the path encloses, then that gives you the Berry phase. Okay. And the Berry phase is equal in a Phil-Landau level, is equal and opposite in magnitude to the Bohr-Maharonov phase an electron would have going around the same path. Okay. And the other thing about it is if there's another empty orbital in the path, the Berry phase is reduced by 2 pi. And since these objects, the empty orbitals are identical objects, they can exchange, you pick up a phase factor of -1. So we see that the empty orbital is in a Phil-Landau level is a fermion. So let me fill that orbital. What have I done? I've taken an electron, which is a fermion, added it to the orbital, which is a fermion. Clearly, I've got a boson. Indeed, if I pull this composite object around the path, the Bohr-Maharonov phase cancels the Berry phase of the hole. And if I exchange them, they're a boson. In this case, in a Slater determinant, if I exchange a filled orbital, if I exchange 2 filled orbitals, I'm exchanging both the orbital and the particle. So I get a -1 for exchanging a row of the Slater determinant and -1 for exchanging a column. So it's obvious it's a boson, right? This kind of language would never be applied to Bloch states because the orbitals aren't identical. Orbitals are distinguishable. They're distinguishable in Bloch bands because they're glued down in the unit cell, and I can label each orbital by which unit cell it's in, kind of like in solid helium. I can label each atom by which unit cell it's in. So essentially, the properties of liquid helium-3 and helium-4 are essentially similar, apart from the nuclear magnetism. So similarly here, but this is a language only appropriate because the orbitals themselves became dynamical objects and identical and obey identical particle statistics. This arguments generalize completely to the fractional case. It's a bit like in 1 dimensions. You can have discuss ideal gas in 1 dimension in Slater determinant language or in the bosonized language. When you switch on the interactions, you can't use the fermion language very easily, but the bosonized language has an immediate, simple generalization to the interacting case. This is similar in the quantum Hall effect. So in this thing where the background is P over Q, the basic object is this hole, which is size Q hole. This object is controlled by a Chern-Simons field with the Nobelian U1 level K Chern-Simons, and the integer is P times Q. And then I add, so the Chern-Simons theory is actually describing the hole before I put the particles in. Okay, the composite system is now to put some charges inside the hole. This actually will couple it, because now the Chern-Simons field, as it moves around, it drags charge with it. It introduces a coupling between the Chern-Simons field or the composite. It is a coupling to the electromagnetic field, and I get the quantum Hall out of it. So the rule is, which used to be called the odd denominator rule, which is more general now, is that the total object has to be a boson to condense, so -1 to the K times -1 to the P for exchanging P electrons has to be +1. And it could also be -1, but when you get composite fermions have the same structure, basically, but now they're not going to condense into quantum Hall states. Okay, let's move through. See what I've got here. Okay, here's a point about the Chern-Simons gauge theory. Okay, so the Chern-Simons gauge theory, we've got the topological term linear and time derivative in the Lagrangian, and we've got the flow of the voids or the bubbles, and this is the density in the current. And then if I put a charge EB inside the object, it now couples to the electromagnetic field. One interesting point, I'm going to run out of time soon, is that there's a whole lot of stuff which I regard as nonsense, which was sort of vaguely died out. A lot of focus on the so-called gravitational Chern-Simons term, which people were trying to add and trying to do something with in quantum Hall. One interesting thing is this action is correct. I should not Often people from a conformal field theory or field theory background want to put a square root of determinant of the metric in front of that, where the metric is whatever is used to set up the coordinate system. That's incorrect in this case because quantum Hall systems and topological systems in general, there's no kind of dilatation business in it. They're not conformal fields. They're the opposite of conformal field theories. They're completely rigid. What? 5 minutes. They're completely rigid against compression. So typically topological gap systems don't have incompressible. And so to inherit, there's a lot of baggage from conformal field theory that gets inherited in treatments of that, but they're not critical systems and conformal systems, so you should not have this. You should actually be always working with the determinant one metric, which is defining, only used to define coordinate systems, or if it's a variable of the system, would be used to define a shape. So anyway, there's the thing of that. So here's a picture quickly of the Laughlin state. You've put one electron in the center of this group 3 thing, and that's the composite. The 2/5 state, I've got 2 and 5. And interestingly, if I dope a 1/3 Laughlin state, what I'm doing is actually, let's go there. If I dope the Laughlin state, kind of like doping a semiconductor, I add one charge to it. Initially, it will go into one of these 3 orbital plus 1 composite bosons, gets turned into an object which is a fermion, which is two particles in the 3 size object. But that's energetically unstable. It likes to lower the charge density locally, and it will split up by grouping with 4 other states. And the 2/5 droplet I showed is actually the quasi-particle of the Laughlin state. And okay, let's go back. So if I lightly dope the Laughlin state, I've got a low density of these 2/5 objects, which are not condensed because but the charge carrier doesn't, the charge does not move by the flow of the 2/5 droplets. It moves by the hopping of a composite fermion between these two. So these droplets are like unit cells. The composite boson is the analog of the unit cell in a solid. And when you dope it, the mobile charges are actually composite fermions. So what actually happens here, a composite fermion will hop, and then you'll have transformed this one to a 2/5. Let's go forward again. Let's stand out. And in fact, there's this whole Jane picture, which is called pseudo-Landau levels. In fact, if we look at it more closely, we can see by the composite fermion is 1 particle in 2 orbitals, if you're above 1/3 filling. And in the region between 1/3 and 1/5 filling, centered on 1/4, the composite fermion is 1 particle bound to 4 orbitals to form a complex. So if I go up in the sequence, I absorb one composite fermion of the 1 in 2 variety takes me to 2/5. Absorbing another one takes me to 3/7. I can see that's got somewhat of an analogy to adding electrons in 1, 2, 3, 4 Landau levels in the integer Hall effect, but I'm not going to call this Landau levels, okay? And the same algebra going down, you add 1/4 to them, and you go below 1/3, and you go 1/3, 2, 7, 3, 11. So quite interesting. So let me just finish up very quickly. Some new ideas. Composite fermions also have quadrupoles. And one of the outstanding problems is the nature of the state at half filling of the Landau level, which is a particle hole symmetric composite Fermi liquid, okay? And various attempts, Halperin, Lee, Reed, and more recently Son, various people have tried to come up with some kind of description. There's no wave function yet to go with it, although various model wave functions, such as one called the T-Pfaffian, which was supposed to be a quantum Hall state, is actually a good approximation to it numerically. But there are actually 2 kinds of composite fermions now, near 1/2. If I'm coming from the bottom, I can make a composite fermion I've got a size 2 hole and I put an electron in it, in the middle. Coming from above, I've also got a 1/2 fermion. The particle hole transform is actually just that one. I put the electron in the second orbital, not the first orbital, okay? So actually 2 species of composite fermions at 1/2. So the calculations of the supposed Fermi surface area was wrong if you were thinking only 1. And they have opposite parities. That's starting to smell like the Dirac proposal. So these two are both 0 momentum states, and they have opposite parities, so they can not mix if k equals 0. Okay, and interestingly, two of the below 1/2 ones can bind, and they form a composite boson, which is the Pfaffian state, and they've doubled the amount of quadrupole has doubled by doing that. If the energy is gained by forming quadrupoles, you see very strongly the binding energy that would form that thing, etc. Some similar thing. So the particle Hall symmetric composite Fermi liquid has, if I don't want to form quantum Hall states, it's got equal numbers of these guys. You actually have to make them all slightly different, give them momentum. Momentum in the magnetic field is the same as dipole moment, essentially. So by these two things have opposite parity. So by mixing them a little bit, so I mix a little bit of this one of one into the other, I will actually make an object with a dipole moment. An interesting picture of the composite Fermi liquid, which I see my time is up, will be a mixture of these two things, and we can actually start to count how many states I can make, and I got a result that initially was very disappointing to me until I realized it was actually not disappointing. If I now, these things form a Bloch sphere. So by counting the maximum dipole, actually I can count how many momentum states there are. By converting dipole to momentum, I convert them to K. By multiplying by the area over 2 pi squared, I convert to the number of electron states. And indeed, I find that the number of states corresponding to the diameter of this Bloch sphere is 1/4 of the number of flux quanta, or half the number of electrons. So there are actually two kinds. So the number of states I get here is exactly right to accommodate both each of both kind of composite fermions completely. So there seems to be nothing left over for a Fermi surface. Interestingly, this is a very interesting kind of band. It gets around a lot of all the problems people had in visualizing composite fermions, because when I get to the equator, the positive and negative quadrupole things become equivalent. So the two bands kind of merge and terminate at the equator. And the shape of this object is actually the shape of the quadrupole of the composite fermions, which as I kind of implied, was actually a thing that can fluctuate with an energy cost. So actually, this is the ring around the equator, which is the analog of the Fermi surface. It's a boundary above of which there's nothing outside it, is actually, I can think of it in the fluctuating Fermi surface picture, and I believe that will be where the low energy excitations of this gas will come. So this actually leads to a very new, and I think a convincing picture of the Fermi. Son had like a Dirac point, something going down to -infinity here. He said, I only need to think about the one Fermi surface, and he thought particle Hall symmetry was just a relationship between this point and that point. That doesn't make sense. Here, the particle Hall symmetry is a relation between here and here. But anyway, this has a Dirac-like feature to it. This has a Dirac point in the middle, where they have no momentum or dipole moment and opposite parities. So I believe this is probably going to turn out to be the correct picture of the composite Fermi liquid 1/2, and it comes about from considering the quadrupolar nature of the things. And okay, thank you for letting me use up my time.
Okay, so we have sort of run out of time, but if there is a quick question. Okay.
I have this Landau mixing related question. So in a conventional magnetic field, when I have in presence of magnetic field, we have this Landau level mixing. And then they related to issues. But in a Chan band where I don't have those Landau labels, shall I think about this Landau label mixing problem? Do they exist, or the different kind of pictures shall I?
I'm not sure what the question was, but the Landau level mixing here is the electric field causes Landau level mixing. So actually, if these things are in, I mean, one issue has been, interestingly, okay, I probably don't have time to go into this thing, but yeah.
So in the picture you showed, you said that the composite fermion Landau levels or pseudo Landau levels, there are some effective or fictitious, but why does, from the composite boson perspective, how do you see that the cyclotron gap comes out to be consistent if it's the fictitious object?
It's essentially a renaming of the picture, but I don't think there's any consistency in the. I think the notion of lambda levels, it's only justified on the basis of it's a good trial wave function. I don't think the physics. I mean, but I can certainly see that that creating the bigger composite things by adding this, the structure of the composite boson is like you're filling the first n orbitals in 2n plus 1 fluxes.